Hello, my name is Ilyan Todorov, and in the next hour I'm going to talk about molecular dynamics. It's an introduction to non-computational scientists. The slides have been prepared with the help of Rosen Apostolov at KTH Sweden, and I work at STFC UK. So what is computer modeling? It is used to provide insight and understanding of how complex systems behave, beyond what theory and experiment could deliver separately. It bridges theory and experiment by solving some equations that describe the state of matter numerically. So because we have to do this numerically, the best tool to use is computers. And computer simulations are used as an assisting tool by scientists and engineers to verify or predict experimental observations as well as test and or tune theoretical models. So you can see the picture to the right at the bottom that we have this triad of theory, experiment and computation, and right at the middle, when we use all of them, we have a solution to the problems that we want to address. So computational science is a generic term for any field of science where computer simulation is used in conjunction with theory and experiment to model various aspects of reality, to provide solution to problems and answer to questions that often cannot be satisfactorily explained by theory and experiment alone, and sometimes together, because phenomena cannot be observed directly. Experiment doesn't provide the resolution in time and space, and theory is too complicated to be solved analytically, so we have to resort to the use of computers. And within natural sciences, one could outline a number of fields which generally resolve behavior of nature, the physical world around us, on different time and length scales. So we have physics, chemistry, materials and engineering, and various other sciences, and quite often some of those overlap. So what is the purpose of modeling and simulation? There are two primary roles. Test models which explain experiments and test theoretical predictions. The driving force is that computers are fast enough for numerical experiments. Most models are also too complicated for purely theoretical reasoning. As I said, analytical solutions are too expensive or impossible to achieve. And there are phenomena which cannot be observed directly by experiments. On the diagram to the right, you can see a simple explanation of how we can start from real liquids and start making models or perform experiments and get down to test of models and test of theories, where if the model is too complicated, we can construct an approximate theory and test whether the approximations that we have made or presumed are correct for the certain scenarios. The purpose of this talk is computational chemistry and computational physics, but quite often it's called computational chemistry because it uses computers to aid chemical inquiry. It generally involves methodology and theory to model systems on the atomic scale. So generally we have a number of methods that are divided into ab initio methods, semi-empirical methods, or molecular mechanic methods using classical mechanics. The ab initio methods are the most accurate and versatile, but they're computationally very expensive. So they give very good results for very small systems, let's say 200 atoms. The semi-empirical methods are those that use approximate quantum mechanics. They rely on empirical or ab initio parameters. They're affordable and accurate, but limited to the correct, well-defined problems for systems with about 1,000 to 10,000 atoms. And molecular mechanics methods are the cheapest ones. They rely on empirical force fields, which are not absolutely correct for all possible conditions, but they're tuned for specific conditions, and they don't account for the electronic properties. They're very affordable and can be used as a virtual experiment. They can handle extremely large systems beyond 1 billion particles. In this slide, you can see a diagram where we move from ab initio methods to classical methods, and you can see that even in the ab initio world, which is where we know something about electrons, we have a number of methods that can resolve those equations of state on a certain time scale and with a certain accuracy. And when we start with the configurational methods like Hartree Fock that are absolutely accurate but very, very expensive, then we can move to quantum Monte Carlo, we can move to density functional theory, and so on, where we use approximations like atomic orbitals. And if you forget about the electrons world, we can go to atomistic simulations, and if that becomes too expensive, now we see that the time scale is very large. We can get access to microseconds, but if you want to go beyond, we can do some coarse graining, and if you want to go beyond that, we can go to finite elements. And there is this gap in accuracy and speed when we don't know anything about electrons. But as we move up, we forget something about the chemistry, we forget something about the small detail. So we have to choose the method that we want for the problem that fits it best. Another picture of the time scales, time and length scales, is this one. So where we can see the 10 to minus 15 seconds, the vibrations of the atoms and the distribution of the electronic clouds around the chemical bonds. That can be achieved only with quantum mechanics simulations. If you want to move up, where we can see how molecules interact together, we can use quantum simulations on molecular dynamics. If you want to see the motion of membranes and ionic channels in membranes, we can still do molecular dynamics. This is in the range from 10 to minus 12 to 10 to minus 6 seconds. And if you want to go up, where we can emulate biological experiments on the same scale as biological experiments, we have to coarse grain our system and forget about the exact chemistry of the compounds in the model system, and we can reach up to billions and billions of particles and emulate viruses, for example. In this slide, we can see a few models of the system, of few model systems which can be addressed using molecular dynamics. So in the first picture to the top left, we can see protein solvation and binding. So this is a protein that binds to a mineral surface. We can simulate how a DNA strand moves around. We can look at membrane processes with transmembrane proteins. Or we can look for drug polymorphs. Then we want to discover different polymorphs that are more useful in the pharmaceutical industry. At the bottom row, to the left, you can see a picture of radiation damage, which is quite important. So we can look at crystalline amorphous solids and test for damage and recovery when we irradiate those. We can see dynamic processes in metallo-organic and organic frameworks. And bottom right, there is dynamics at interfaces, where we're looking at the formation of grains of ice, where we're looking for phase transformations. So, what is molecular dynamics? It is the solution of the classical equations of motion for atoms and molecules to obtain the time evolution of a system. It is applied to many particle systems, since general analytical solution is not possible. Thus, one must resort to numerical methods and computers. It does classical mechanics only, since a fully fledged many-particle time-dependent quantum method is not yet available, and it uses a Maxwell-Boltzmann averaging process for thermodynamic properties, i.e. we are doing time averaging. And you can see in the diagram what the traditional cycle of molecular dynamics is. We have some input data about the system. We have interaction function between the various particles, which we call force field. We have the coordinates of those particles and the velocities. Then we compute the potential and derive the forces on the particles. We update their coordinates using some equation of motion and the velocities as well. And then we collect some statistical data. And we do that for as long as we want. And then we look at the data and we derive some conclusions. So what are the limitations of molecular dynamics? As I mentioned earlier, interatomic interactions, that we also call a force field, are based on parameters and are imperfect because they are derived and fitted for fixed conditions like pressure, temperature, pH, or something that depends on the environment. Transferability of the force fields for mixed environments is an open question. Phase space, something that we're not going to mention very much in this lecture, is not sampled exhaustively by single events or within small model systems. This means that we have to do as long as possible runs and do as many runs as possible. Usually the goal is to sample equilibrium ensembles, not simulate individual particles. Example, free energy of solvation for amino acids often have errors of 1 kilojoules per mole. It's unlikely to calculate binding free energies more accurately than this. Molecular dynamics can only give free energy differences. So we also have limited polarization effects. Waters can reorientate, but partial charges are fixed. Multipolar force fields are needed for more accurate representations of such processes. So what are the example properties that we can calculate? From the ensemble averages, we can have free energy differences, so free energy of binding, solvation, interaction. We can calculate diffusion coefficients, viscosity. We can look at the reaction rates, phase transition properties, protein folding times, structure refinement. Single events for strongly non-equilibrium processes, such as in radiation damage, surface coating, or nucleation, for which we can use metadynamics, for example. So what is statistical mechanics? So just because you see something in a simulation does not mean it is real. As I said, we have to do as many runs as possible and as long runs as possible. Equilibrium properties are all about statistics. So we have to improve the statistics in order to gain confidence in what we are seeing. When you've seen something 10 times, it is significant. If you have seen it only just one time in many runs, it is not. You should always try to calculate error estimates for predicted properties. Environment and transferability. So look at the two systems. One of them is unrealistic biologically, the other one is more realistic. So each force field has their own water potential parameters that work best. For example, we have amber and charm, tip 3P. Choose the one that matches the compound you want to simulate. So also you have to avoid system size effects. So look at one small system. For example, if you have 1,000 water molecules, the number of surface waters will be approximately 500, which is about half of the bulk. And if you have 1 million molecules, then the surface water will be 6%. And this is if you don't have periodic boundary conditions, which we will mention slightly later. So this is about the periodic boundary conditions. What are those? Our model systems are too small, especially with respect to the Avogadro's number. To avoid surface over bulk domination effects, we have to resort to periodic boundaries. So we pretend that boundaries don't exist, and if you have one small system, like this one in the middle, we can say that this system sees itself all around. And it's almost like the Pac-Man game. As you cross from one boundary, so you're coming out here, you're entering in the same box, coming in from here. We have a number of 3D periodic boundaries that satisfy the periodic boundary conditions. So the general one is the triclinic one, which includes the cube and the parallelepipeds, hexagonal prisms, truncated octahedrons, and rhombic dodecahedron. Various boundary conditions can be imposed. Not all of them are periodic, so we can have none, where we have to be really careful about surface effects. We can have stochastic boundary conditions, where we change what is coming in and coming out in the system, which is useful for biopolymers. We can have hard wall boundaries, like pores and capillaries, and as I mentioned, periodic boundary conditions, which are the most popular in the MD simulations. What are the consequences when we have periodic boundary conditions? The system no longer has a surface, so we simulate bulk. The system becomes pseudo-periodic, which it can be used in our advantage for the eval sum. It is incorrect to impose cutoffs on long-range interactions. However, the eval method, which we'll mention slightly more later on, can deal with infinite number of periodic images, specifically when we use particle mesh evals. Correlation in space beyond the half cell width are artificials. For these reasons, the cutoff has to be smaller than half the box width. And correlations in time beyond the length of the box or the speed of sound of the material are in principle subject to reoccurrence. In practice, this does not seem to be the case. And we have to use the minimum image convention, which is very simple to explain, as you can see in the next slide. As 3 slides ago, we saw that as we come out from the box on one side, we enter from the other. Because of this, when we a particle that can see another particle within the box can actually see the same particle much closer next to the boundary of the nearby box. We also have, when we calculate the interactions, we have to look at the smallest distance for that specific interactions between particle I and j. And in this case, I will interact with j prime rather than with j. As I said, the cutoff is less than half the width, and the width is L here. So what are the types of interactions that we include in molecular dynamics? For purely chemical reasons, we have bond vibration. We have to account for it with certain potential. We have angle vibrations when we have three particles, or we have torsion potentials where we have 4 particles in a configuration. These are the bonded interactions. The non-bonded one, which we also call intermolecular, are the van der Waals interactions, which are very, very short range, and there is an example of 1/12.6 potential, as we call it, and electrostatics, which is a long-range interaction. These are the charges that those particles bear. We can see the number of different types of interactions of molecules that are connected together via those number of interactions that were presented in the last slide. So we can have point ions in our simulations. Those ions can be polarized. We may also have particles without charges. That's the simplest model. We can have flexible molecules that are interacting together via the bond angle, the hydro, or so on potentials. Or we can have the same molecules but with constraints on them. So the length between them is constrained to a certain length. And we also can pretend that some molecules are rigid, so they move as a configuration together without changing distances between them. So they perform as a rigid body. They move as one, but they can rotate. And we can connect those rigid bodies together. And we can have rigid bodies that are connected with rigid links. Atom types and environment. As I mentioned previously, it's very important to account for the environment. And depending on the environment, the same atom can have a different atom type. For example, if we have a carbon, it can be differently charged, interact differently with the surrounding particles in a different molecule. And you can see that in the diagram. So we can have different atom types even for the same chemical element, which depends on the environment. So force fields and force field builders do account for this, and people shouldn't mix those together. So a set of interactions constitutes a force field. People shouldn't mix force fields except if they know what they do and they're experts in the area. You can see in the diagram how force fields developed since the early 70s, and nowadays we have a number of them, and here you can see the 4 most important of them that have developed over time since Lifson developed his own in the 1970s in the Weizmann Institute in Israel. So we have charm, gromos, amber, and OPLS. There are many more, but these are the 4 most important that people use. I forgot to mention Gromax as well, so 5 most important. And the force fields as a formula look like this. So the potential of the full system comprises all pair interactions, and we name those van der Waals. They include charged interactions that are solved by using Ewald summation. We have some mixed 3+4 body that in this case Thurso, but there's Stillinger, Weber, and so on. We have purely 3-body interactions, we have purely 4-body interactions, and in certain cases we have metal interactions. And for metal systems, it's worth noting, we have an electron gas, so there are no charge interactions, but the metal interactions are fairly complicated. There are many body, which can be split in 2 parts, a 2-body part for the many body, and a density-dependent one, for which the forces on atoms and the energy of an atom depends on the local environment around it. There are other environment-dependent potentials, but in this case we don't need to mention them. So these potentials that we mentioned so far, the intermolecular, and the rest that's displayed in this formula are the intramolecular, which account explicitly for the chemical nature of the molecules and the particles that constitute them. So we have bonds, interactions, angle interactions, dihedral interactions, improper dihedral interactions. We can also have tethers, which is tethering a particle to a certain point in space. And in certain cases, we can account for some polarization effects using core shell models. And we also have external interactions, such as magnetic, electric, gravitational, or we can have containing spheres, whatever users can think of, which are not part of the system. Simple simulation, a simple example of simulation is that of argon. So we have a simple pair potential, either we call it Leonard-Jones or 12.6. You'll see what it looks like in the next slide. It models the Pauli exclusion at short distances. It's very, very repulsive. And the van der Waals forces, which are attractive at long distances. We have a Lagrangian, which is simply the difference between the kinetic and the potential energy of the system. You can see the box of the simulation, and we are centered on one particle, and we have a cutoff sphere around it, and all the particles within the cutoff sphere interact with the particle we have centered ourselves on. And the particle doesn't feel anything about the particles that are beyond the cutoff of that sphere. This is what usually Leonard-Jones potential function looks like. We can see the well of this. So at short distances we have very hard sphere, so the energy goes high a lot, and we have this well here, which has depth epsilon, and the cross with the axis is sigma, and we have some cutoff distance that we impose here, even though the potential goes further. It's very important to pick the right cutoff. Usually we pick the cutoff between 3 to 5 times sigma, which is between 8 and 15 angstroms for real systems. Why do we pick a cutoff? Because on the computer we would like to minimize the time we calculate this interaction, and we know, or we pick it in such a manner that beyond it this potential is very close to zero, and that there shouldn't be any consequences to increasing it. So the equations of motions that come from the Lagrangian for this very, very simple case adjust the Newton equation, and what we need to do on the computer is to calculate the forces on all atoms. And essentially, if they interact by such potential, we calculate the forces by taking first derivative of the potential up to the cutoff. So we minimize the number of particles that interact with the central particle we sit on each time. And after we've calculated the forces, we can start moving the particles according to what their velocities, initial velocities are. If we have charges, then it's a further complication, but the method offers an elegant solution to solve the full electrostatic problem by splitting it into two parts when we're talking about now Ewald summation. So one part is in real space and the other one is in reciprocal space. In real space, to comply with the cutoff concept, it is convenient to introduce a screening function that is added around all charges to make the interaction decay very fast to zero at the cutoff. The added screening is then subtracted in reciprocal space, and due to the periodic boundary conditions, we can use Fourier transforms to solve this problem very, very quickly. So what are the consequences of the introduction of potential cutoffs? So there is a step in the potential at R cut, which gives rise to artificial energy fluctuations. There is a discontinuity in the force at the cutoff, which is large enough, and will show up in the space and force correlations. The above problems can be fixed by using shifted force potentials, and that's the formula you can see on the screen, or by tempering the potential at short distances just before the cutoff to the same effect. The long-range corrections are required for both potential energy and virial in condensed phase studies, and these are easy to calculate. So let's talk again about the key stages in simulation. This is slightly different display of this. So what we start with is the setup of the initial system. We calculate atomic forces, we calculate atomic motion, then we calculate physical properties. And we repeat this process until we gather enough statistics. When we decide we need to stop, we can produce a summary. So the calculation, to calculate the atomic motion, we need to do via integration algorithm. What are the essential requirements for such? So we need computational speed, low memory demand, accuracy, stability, so we conserve energy. There is no drift of energy of the system, total energy of the system. It is a useful property to have time reversibility, an extremely useful property to have symplecticness. We can talk more about this in another lecture, but this will give you some feel of what are the requirements for such algorithms. So the essential idea is that if we start at time t at a certain position, we have a velocity v and a force F, then we will move to position t plus delta t, rt plus delta t, where we have a net displacement that comes both from the velocity and from the force contribution. There are a number of algorithms that can do that. There are two of them that are mostly used, velocity Verlet and leapfrog Verlet integrations. But here we will show only the velocity Verlet, which I think is the most popular one. It often guarantees symplecticness depending on how it's developed. And you can see on the diagram how it is derived and then used in application practice. I don't need to go over the equations, but you can see that all velocities, positions, and forces aligned in time. And in order to obtain, for example, if you move from time step n to n plus 1, we want to get the position. In order to obtain this from Rn to Rn plus 1, we need the force at time step n, we need the velocity at time step n, and if we want the force of time step n plus 1, we need the positions of time step n plus 1, and so on. And you can see how the time is discretized in this diagram. There's a large variety of integration algorithms. The one that was demonstrated in the previous slide was the microcanonical one, where we had constant number of particles, constant volume, and constant energy. However, there are many more of these. The next one would be the canonical one, where we have constant number of particles, constant volume, constant temperature, and there are various flavors of those. And so we can complicate them. The various letters mean various things. So T is for temperature, P stands for pressure, N is for number of particles, V is for volume, E is for energy. Sigma, that we see at the last line, is anisotropic pressure. So now it's a tensor. Pn stands for normal pressure at the surface, which is A, and gamma is surface tension. So the further down we go, the more complicated the integrators become, but their relative cost is very little. So when we have a certain letter in the abbreviation of those integrators, it means that we have a target value of the letter. So for all the molecular dynamics ensembles, it is normal to have constant number of particles, so the number of particles doesn't change, and especially with periodic boundary conditions, we want to preserve the number of particles, otherwise we have to account for the volume they represent, because we have to stay at the density of the particles, the same density of the particles in that bulk that we simulate. So as I said, we have the microcanonical, we have the isokinetic, the Evans ensemble, we have the canonical ensembles with various interpretations. We have the Anderson, Langevin, Peretz, and Zech Hoover, and the most popular one at the moment is gentile-stochastic thermostats. And for the isobaric and isothermal ensembles, we have Langevin, Beretson, Zech Hoover, Martino, Tuckerman, and Klein integrators. And then if we move from isotropic pressure to anisotropic, we have the one with the pressure tensor and sigma t. And if you want to simulate interfaces for or membranes, we have NPN80, which is normal pressure, constant surface, constant temperature, or NPN gamma T, which is normal pressure, constant normal pressure, constant surface tension, and constant temperature, again in the various flavors as the ensembles above. Something about the integration algorithms: when we include temperature and pressure, we are coupling equations that have their own timescales. And in order to couple to the particle dynamics, these need to be these timescales need to be slow enough to control the oscillations in temperature and pressure, but not too slow in order to reach equilibrium at target temperature and pressure in reasonable amount of time. It is a user choice, but quite often the user needs to think and relate those scales to experimental data. So typical relaxation constants for biochemical simulations are 0.1 picoseconds for the thermostat and 5 picoseconds for the barostat. And you can see the oscillations of the box size, so the volume down here. And you can see the three curves in the graph that represent the three different sides of a parallelepiped when a box is simulated. And at the start, when we're not equilibrated, those are not the right ones, but as we approach equilibrium, we can see that they set a default value. So the change, the largest change is in the z direction of this box, in this particular example. The system properties that we can obtain from simulations is kinetic energy, and from there we can obtain temperature. We can obtain the configuration energy, that's the total energy of the system. We've displayed the formula of that energy previously. We can obtain the pressure, and we can obtain specific heat. We can obtain some properties such as the radial distribution function. We'll talk a little bit more about it. The structure factor, and the structure factor is something that is also available experimentally from X-ray diffraction or neutron scattering. So what is the radial distribution function? It is a property that says how the system density varies in space if we sit on one particle, and it says something about the structure and how things are layered around the particle. So it says something about the environment. Lots of properties can be derived from it and from the structure factor. So this is a simplification of how we calculate it. We sit on a particle here at the center, and we calculate what the density is in the volume between two spheres with slightly different radii, and the difference between the radii is delta r, and we can do that consecutively, starting from a very short distance around the particle and going outwards. And of course, we can only calculate this up to the cutoff distance. If you want to go beyond, we have to increase the cutoff, and that increases the computational expense of the virtual experiment. And this is what a typical radial distribution function looks like. We see a few peaks, which will, if our particle is here in the center, what we see is the first layer of neighbors around this particle right here, then the second, and so on. And as we go outwards in space, the radial distribution function has this property that goes to 1 when we go to infinity. And of course, we lose more of the structure as we go further away. So again, more about the neighbors here. Even though each point of this graph has a meaning, when experts look at the peaks of that function. So there are other dynamic properties that we can calculate, easily based on correlation functions of the form shown here. And the two that I need to mention are the mean square displacement, which shows the Einstein relation, or the velocity autocorrelation from the Green-Kuber relation. And this is what the mean square displacement is like for two different systems. For liquids, it always goes up, and for solids, it stays constant. Of course, the first part here is when the system starts, we need to gather enough statistics in order to get on the line. We also can show the velocity autocorrelation function. This is an example of it. And we need to talk about what the limitations of molecular dynamics are. As I mentioned, it's not the most exact method, but we can do a large amount of particles. We can simulate large number of materials, and we can look at large phenomena on various time and length scales. So as I mentioned, parameters are imperfect because we derive the potentials that we use for the interactions between particles with ab initio methods for certain state points like pressure, temperature, pH, and so on. We do not sample phase space exhaustively, and this is because we want to stop at some point. When we are confident in our result, we don't need to run forever. And as life doesn't stop, a simulation shouldn't stop. But if we have what we're looking for, there is no need to continue. At the end of the day, it's answering a hypothetical question, and we construct the simulations in such a way that we achieve the result in the shortest possible time. An example of not sampling exhaustively is that free energies of solvation for amino acids often have errors beyond 1 kilojoules per mole. But even if we could do the calculation to infinity, still there is an error bar that we always associate with the method or the force field that we use. So it is likely that it's impossible to calculate binding free energies more accurately than this, though force fields exist that claim that we can. However, these are very computationally expensive. Also, we're limited in the polarization effects. Waters can rearrange, but partial charges are fixed. However, simulations, molecular dynamic simulations, are cheaper than experiments. They're more easy to set up, to repeat, with slight changes in the initial conditions or changes in the force fields, and thus they serve as an invaluable testing tool for scientists. How to use molecular dynamics? We have to think first and then simulate. We have to ask specific questions like which set of molecules binds best, and try do various simulations, then compare with another one, which material recovers better or faster under radiation. Simulate 10 models and then compare whether they act the same and what the differences are, and simulate them a number of times in order to gain confidence that the result that we have seen is actually it. We're trying to answer A-B type of questions. Does histidine to arginine mutation affect stability, or does replacement of zircon with lead in pyrochlorous affect the recovery processes? So it's a testing tool. We have to ask questions, and we have to construct or set up systems that will provide us with answers that will help us understand whether the answer of the question will lead us onto it. So what we do if we want to go beyond classical MD scales? The atomic scale is not always the best choice when trying to access phenomena occurring on a larger time and length scales. There are a number of ways that one can employ to strengthen the argument and modify the equation motions in molecular dynamics. For example, we can reduce the degrees of freedom. One way to do this is to rigidify part of molecules and then use rigid body mechanics, where we have 3 degrees of freedom for motion of the rigidified bit of the molecule and 3 degrees of freedom for the rotational motion. However, if you want to look at congregation of particles as one particle, this is type of coarse graining. We can reduce the degrees of freedom in that way and use methodologies like dissipative particle dynamics, or just use coarse grain molecular dynamics. These simulations will be cheaper to run because we have reduced the degrees of freedom that describe the system, but some of the fine grainness of the system will be lost. So some of the chemistry will be lost, some of the small scale details, but we compromise because we're looking at phenomena that, for which those small details are not important. And of course, when we do this mimicking, we will lose the accurate timing. However, we can relate to real timing later on, and it's not important whether something happens on a time scale of 5 seconds or 10 seconds. If we know it happens on the scale from 1 to 10 seconds, it's important to see that phenomena using the methodology that we have. So, of course, if you look at accuracy of timing, we can perform more exact experiments, but you have to pay more in computational time. So, particles will be a congregation of atoms and may even have a shape in a simulation, and if they have a shape, they can also interact via non-sterically symmetric potentials. Another way to ask questions for rare processes and speed up timescales, processes such as nucleation, vacancy hopping, defects annihilation, protein folding, crystal phases in emergence of crystal phases in emulsions, is to extend the dynamics using advanced methodologies such as temperature-accelerated dynamics, hyperdynamics, or metadynamics. So there are a lot of methods there, numerical methods that can help you go beyond the classical MD scales. However, for those, a lot of chemical or physical intuition needs to be employed, and the questions have to be asked very, very carefully. So think about what you want to get out from the simulations, predictions and explanations. And in the last slide, before I finish, you can see a number of books that you can read in order to improve your understanding about molecular dynamics. Thank you very much for your attention.